Our goal for today is to be able to look at a graph and take important information away from it. So to start off with, we want to learn how to describe where a graph is increasing, decreasing, or constant. Now, this is something that you already understand intuitively just from what we know in past years about slope. So if we look at this graph, we start off, our graph is decreasing, constant, and increasing. But we want to know, how do we write this? So first, a reminder, we're thinking about this as you move from left to right on the graph. The graph is increasing if it is rising from left to right. The graph is decreasing if it is falling from left to right. And finally, the graph is constant if it is not rising nor falling. Now, in order to describe this, we are going to think about the domain of the graph for all of the x values. And we're going to take the x values and we're going to split them up based on what's happening. So the graph starts here, it changes here, and ends here. So you can see we've taken our graph and broken it up into 1, 2, 3 separate pieces. So in this first segment, it is decreasing. Here, it is constant, and here, it is increasing. Now we're going to use interval notation to describe these 3 separate intervals where the graph is moving. So first, talking about increasing, that was from here to here. The graph was going up. So x values started at -1 and went until 1, 2, 3, 4. So from here to here. So starting at 1 and going to 4. Now in order to talk about the graph increasing, we're actually moving along the graph. So the single number is not included. So we use parentheses. Decreasing. So we have -1, 2, 3, 4. So from here to here, the graph is decreasing. From -4 to -1. And finally, this middle portion is where it's constant, from -1 to +1. So a few things you need to remember. First of all, each of these numbers represents x values, where it's happening, not the y values. Also, this is interval notation, so these are not points. And the final thing to remember is that whenever we are describing these intervals, we will always use parentheses, never brackets. All right, let's try these examples down here, see how we do. So we're always thinking about our x values, moving from left to right. So if we trace it, this graph is constantly increasing. Now I can see here in the middle, it looks like it flattens out, but this is actually our cubic function. So as you plug in bigger numbers, the y values get larger. So we could say that this graph is increasing on the interval -infinity to +infinity. Because as we go to the left, x is starting at -infinity all the way to the right at +infinity. Push pause, try the next two, and then come back and check your work. Okay, so our x values is what we're looking at. Our graph starts here, changes here. Here it's decreasing, 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 so it changes here and ends here. So on this portion, the graph was increasing. Here, it's decreasing. Here, it's increasing again. So we'll write increasing on the interval. So from -2 to -1. Next, it's decreasing on the interval. Okay, so that's from -1 to +1. And now for this last segment, it's increasing again. So you could rewrite this, or we'll just add it on. And 1 to 2. For our last graph, it changes, or it starts here, changes here, and then it keeps going so it never ends. So the graph starts off increasing, here it's constant, and here it's decreasing. Okay, so this is increasing from, maybe you could estimate that, maybe -2.4 to 0. It is constant from 0 to 2, finally decreasing from 2, and remember the x values is what we're looking at, so forever, to positive infinity. Another piece of information we want to be able to take from a graph are the maximums and the minimums. So we're talking today about relative maximums and minimums. Now I know minimum means lowest, maximum means highest. The relative comes in because it means within that portion of the graph. So if you look at this graph, the two lowest points happen here and here. So those are the minimum points. However, right here, this point is the smallest point in this general area of the graph. So all three of these would be considered relative minimums. So if the function has a relative minimum, it will appear as one of the low points on the graph. So here, here, and here, all three of these are relative minimum. On the other hand, if the function has a relative maximum, it will appear as one of the high points on the graph. This one has 2, here and here, are relative maximums. Now from the picture we see this and this are also high points, but the arrows indicate that the graph continues to go. So we do not consider these to be relative minimums because the graph continues to increase even beyond that. Alrighty, next up, let's review the vertical line test. This is something that we've had a lot of practice with. So just a quick review here. Put some arrows at the ends of these graphs. So we've already talked about, in order to be a function, a relationship must show that each input has only one output. So in this case, it says use the vertical line test to decide whether the graph represents y as a function of x. So this is showing us that x are the input and the y's are the output. So by doing the vertical line test, what you're really checking to see is that each input, or x value, only has one output at each point. And so you move your pencil across the page, or your finger, or your imaginary vertical line, whatever, to make sure that every single x only has one y associated with it. This one passes the vertical line test. So we'll say yes, it is a function because it passes the vertical line test. Our next graph, on the other hand, fails it. If we were to draw a vertical line, it touches the graph in more than one point. So in this case, the input of 1 has two different outputs, positive 2 and negative 2. So we'll say no. It fails the vertical line test. And finally, this one here, as we look, it passes. Our last piece of information for today are zeros of a function. Now, a zero of a function is an x value that's going to make y be 0. So you might remember those as x-intercepts. So if the graph of a function has an x-intercept at a certain point, a0, then a is called a zero of the function. So the zero of a function are the x values. It's the zeros of a function are the x values for which y equals 0. So to find these, we're going to go to each equation and we're going to replace y with 0. Then you need to use your algebra skills in order to solve these. Now the first one can be solved either by factoring or by using the quadratic formula. Let's go over this one. In order to get rid of the square root, we would square both sides. So 0 equals 10 minus x squared. Next, we have to get the x by itself, so we could add x squared to both sides. And finally, square root. Don't forget your plus or minus. So this function has two zeros, positive root 10 and negative root 10, because if you plug those into the equation, the entire equation would equal 0. When you have a fraction equal to 0, you need to get rid of that denominator. So we're going to multiply both sides by t plus 5. So on the right side, these divide out to make 1. We are left with 2t minus 3. On the left side, careful here, 0 times anything is just 0. So we solve this and we get 3 halves. So this function has 1 0 at 3 over 2. And finally, this first one, so you can check your work, see if you got it right. We factor it, we get 3x minus 5 times x plus 2 equals 0. Do the zero product property. And we have two solutions for this equation, which means this function has two zeros, 5/3 and negative 2. You want to make sure that you have your factoring up to par, because we are going to be doing a lot of it this year.